Hello, we talk about syllogism. Syllogism is a sort of argument that contains quantifiers. Quantifiers like all or some or none. For such an argument, we can construct a truth table. We solve it by means of pictures, so-called Euler diagrams. So let us consider this first argument. All birds can fly. Chicken is a bird. Chicken can fly. So we represent every sentence by a picture. So these first two sentences are called premises, and this is the conclusion. So in the first sentence we have all. It means that the circle representing birds must be completely inside the circle representing the things that can fly, or flying things. All birds can fly. All birds are inside flying things. So we represented the first premise. Second premise, chicken is a bird. It means that one bird, just chicken, must be represented by a point, is a bird, means that this point must be inside the circled bird. Now let us see what about conclusion. Chicken can fly. Chicken is situated inside the circle representing flying things. It means that our picture satisfies the conclusion, so the argument is valid. Let us consider another argument. There's also a syllogism, since we have all here, the quantifier all. All birds can fly, so we start with the same picture. All birds are inside flying things. Sparrow can fly. The second premise can be represented in two different ways. So we can put sparrow in this part of the circle flying thing, or let us take another picture here. So flying things, birds are inside flying things, but sparrow can be situated here. Although we know it can fly, but this premise, the second premise, can be represented in two different ways, either inside birds or outside birds, since the second premise only states that sparrow can fly. So, and if sparrow is represented here, outside of birds, of the circle representing birds, then the conclusion is not satisfied, since this picture shows that sparrow is not a bird. So this argument, this syllogism, is invalid. Syllogism contains the quantifier some. Some cars are red, some cars have 4 doors. Therefore, some cars are red and have 4 doors. So with some is not so easy as with all, because we have different ways to represent some. The most obvious one, two circles that partially overlap. So we have one circle for cars and another for red things. But we can represent the first premise with some in a different way. This circle can overlap completely. So cars can be inside red things, or red things can be inside cars. All these three possibilities represent the quantifier sum. Some cars have 4 doors. So again, we have a lot of possibilities how to draw the circle for 4 doors. So the important that this third circle must overlap with cars. So 4 doors things, or it can overlap differently. We can, for example, this circle, this picture can be completed by drawing this third circle with not overlapping red things or partially overlapping red things or completely overlapping. So 1, 2, 3. So I have drawn 3 different variations for this third circle on one picture. When we work with a syllogism containing some or any other syllogismic pictures, we can prove that syllogism is invalid by only one picture that shows that the conclusion is not satisfied. If we have a valid syllogism, we should draw all possible pictures and prove that all possible pictures show that syllogism is valid. But if you can find one unique picture that proves that it is invalid, is enough. So let us try find such a picture. So we must add the third circle for 4 doors vehicles so that it doesn't satisfy the statement some cars are red and have 4 doors. So in this case, this second picture is okay with the conclusion. Third picture is okay. But the first picture shows that some cars have 4 doors but are not red. We can draw the picture for 4 doors things also here. Some cars have 4 doors. Some cars are red. Both premises are satisfied on this picture. But some cars are red and have 4 doors is not satisfied. So this picture proves that the syllogism is invalid. As well as this picture, but here it is combined with some other. With this middle picture, we cannot prove that the syllogism is invalid, but we need only one invalid picture and the syllogism is invalid. Some students work in summer, Katie works in summer, therefore Katie is a student. So first we have some can be represented in different ways. Students, person working in summer. So again, Katie works in summer. For this picture, we can put the point representing Katie either in this part of the picture or in that. So let us make 2 variations of this picture. Students, summer workers. So and Katie, so the premise is Katie works in summer. So Katie here, or here. We can two possibilities to where to put this point. And if the second picture satisfies the conclusion, yes, Katie is a student, the first picture does not. So from this picture follows that Katie is not a student. It means that the syllogism is invalid. You don't need to draw all possible pictures here. So with other representations for some, since from this picture we can see that the syllogism is invalid. I remind you that not every argument is a syllogism. Syllogism are the argument containing all, some, or none. For example, here we have an argument, but it is not a syllogism. If I go outside, I will take a car. If I take a car, I will listen music. If I go outside, I will listen music. We can represent this syllogism symbolically. Let us call I go outside P. I will take a car. Let us call it Q. So then the first premise can be written symbolically as if P, then Q. Second premise, if I take a car, so this is Q, then I will listen music. Let us call this statement R. So the second premise can be written as follows: if Q, then R. If car, then music. Then the conclusion. Therefore, if I go outside P, then I will listen music. This is the statement R. So we have here if P, then R. So, and this is a known form of the argument called law of syllogism. And it is known that this argument must be valid. So it means that this argument is valid. It is not always the case that we have the standard form, law of detachment, law of syllogism, or something else. You don't have to remember all of them. Sometimes the argument is something different. In this case, we must construct a truth table. And to look by means of truth table to determine whether the syllogism is valid or not. So then in the truth table we will have to construct. So we start with the column for P and Q, then and R also. If we have three variables, then we will have 8 lines. And then we will need a column for the first premise, if P, then Q, column for the second premise, if Q, then R, and the column for the conclusion, if P, then R. So true, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. So if P then Q, P is hypothesis in this statement, and Q is the conclusion. If the hypothesis and conclusion both are true, then the conditional is true. In the situation that hypothesis is true and conclusion is false, conditional is false. And when the hypothesis is true, then conditional is, if a hypothesis is false, conditional is true, doesn't matter what is the conclusion. So the second column, if Q, then R, hypothesis is Q. When it is true and conclusion is true, we have T. When hypothesis is true, conclusion is false, we have F. Hypothesis is F, we have T. And the same T, F, T, T. So for the last column, we don't need to know every truth values in this value in this column. We consider only the columns, the lines where both premises are true. This line and this line. And here. This and this. So in 4 lines, both premises are true. For these lines, we need to find if P then R. If P then R. It's difficult, 2 different columns, so true, true, T. Then in that line, hypothesis, in all these 3 lines, hypothesis is false, so conditional will be true. So in all the lines where both premises are true, the conclusion is true. It means that the argument is valid. So we knew that because it is the law of syllogism. We made this table just for more practice with constructing truth tables for conditional. Thank you, bye.